Something just happened on the sun that we were never prepared for. A 1.9 X flare, one of the most powerful types of solar explosions we can measure, erupted without warning. And now, millions of people on Earth may be at risk. Before we go any deeper, make sure you subscribe, because what's coming next could affect every single piece of technology we depend on. Tonight, we're diving into a story that feels like science fiction, but every part of it is real and unfolding right now. A massive solar flare, grounded airplanes, satellites glitching, and warnings quietly circulating inside space weather centers. This isn't just a bright flash on the Sunday. It's a chain reaction that scientists at NASA's Solar Dynamics Observatory, the European Space Agency, and even private aerospace companies are scrambling to interpret. And if you think this is something that happens up there and not down here, just wait. Because the signals we're getting from space weather tracking stations hint at a problem that modern society simply isn't built for. Let's take this slowly and piece together what really happened. The first sign came from NOAA's Space Weather Prediction Center shortly after midnight. Instruments picked up an abrupt spike in soft X-ray flux, something only the strongest solar flares produce. Then the number settled. Then it climbed again. And before analysts could even complete the normal classification procedure, the flare intensity jumped to 1.9 X class, a level powerful enough to disturb radio communication, affect satellites, and in some cases, damage unshielded electronics. At almost the same moment, engineers at Airbus began reporting something strange from airports in Europe and Asia. Over 5,000 aircraft systems flagged simultaneous software faults. Pilots were suddenly locked out of certain onboard functions. Ground crews couldn't synchronize telemetry. Navigation updates stalled for minutes at a time. The official statement said, "Solar activity-induced malfunctions." But that explanation barely scratches the surface. Because the flare was only the beginning. Behind it, new sunspot regions, active and unstable, started rotating into direct view of Earth. According to researchers at Stanford's Solar Physics Lab, these regions have magnetic fields twisted so violently that they resemble the same patterns recorded before the Carrington event in 1859, the most powerful solar storm ever observed. Satellites orbiting Earth, like the ESA's Swarm constellation, also detected sudden increases in high-energy charged particles. And deep space probes like Voyager 1, even though it's more than 24 billion kilometers away, showed subtle noise in telemetry consistent with solar interference. But the most unsettling warning came from something unexpected, a geophysicist named Stephen Burns. His work with the Harvard-Smithsonian Center for Astrophysics involves long-term monitoring of solar cycles. And he noticed something that most people would ignore. Small, sharp fluctuations in geomagnetic field readings that don't match normal X-flare signatures. He described them as short, aggressive, and synchronized, almost like the sun isn't releasing energy. It's pulsing, isolating. What does that even mean? To understand it, you have to zoom out. When a solar flare erupts, it sends out more than just light. It sends out coronal mass ejections, electromagnetic waves, charged particles, and in extreme cases, shock fronts that can distort Earth's magnetic field. Usually, these disturbances spread out. But this flare wasn't spreading. It was focusing. And that's where the real problem begins. Because in today's world, where everything from food distribution to hospital care relies on microchips, GPS, and stable electricity, a focused geomagnetic pulse could trigger failures across entire regions. This isn't paranoia. This is what the European Southern Observatory warned about last year. It's what the Vera Rubin Observatory detected during earlier solar storms. It's what Hubble's spectrograph records hinted at during solar cycle 25. And now we're watching it all unfold again. Only this time, the flare is stronger. The active regions are bigger, and the world is far more vulnerable. Here's where the story shifts from interesting space news to something much more serious. Because the flare didn't just release energy, it triggered a reaction in Earth's magnetosphere that scientists are still arguing about. 3 major warning systems fired simultaneously. Ground-induced current monitors in Canada, anomalous voltage spikes detected near Finland, and sudden radio blackouts over parts of the Pacific. Stephen Burns called it a coordinated geomagnetic surge. He believes this flare may be the first sign of a rare magnetic coupling event, where multiple sunspot regions interact to generate repeating pulses of energy toward Earth. If he's right, the 1.9x flare was only round 1. And here's the chilling part. There is no off switch for the Sunday. No update. No software patch. No reboot. We can't block the radiation. We can't shield the entire grid. We can't recall every satellite already in orbit. This is one of the few global threats humans simply have to endure. And the most advanced warning system we have, the Solar and Heliospheric Observatory, can only tell us what's coming, not stop it. So the real question becomes, what happens if the next pulse is stronger? What if the next flare isn't a 1.9, but a 3 or a 5 or higher? We're heading into uncharted territory, and the people who study the sun for a living are starting to sound nervous. All right, let's slow down and really walk through what scientists know and what they fear. Solar flares come in 3 classes: C, M, and X. X class are the strongest, and each point above 1 is exponentially more powerful. A 1.9x flare is already at the edge of what satellites can safely handle. But what scares researchers at JPL and the Johns Hopkins Applied Physics Lab isn't the flare itself, it's the timing. Because this flare erupted during a period of rising solar cycle activity, meaning the sun is becoming more unstable. And the new active regions rotating into view look like something from the late 1950 seconds, when power grids in Canada and the UK suffered major damage. But here's what's even stranger. Several instruments detected non-linear radio spikes, signals that don't match standard plasma eruptions. The Arecibo Legacy Archives contain similar spikes from only 2 events in the last century. That's why some astrophysicists believe Earth may be entering a phase where the sun could produce repeating high-energy bursts. Not enough to destroy civilization, but enough to knock out satellites, disrupt GPS, damage transformers, and interfere with aviation. Which brings us back to the airplanes. Airbus didn't ground 5,000 aircraft because of software. They grounded them because the flare caused cross-system sensor mismatches, something usually only seen during cosmic ray bombardment. If this becomes common, global air travel could face unpredictable disruptions. And that's just one industry. Imagine hospitals losing equipment. Imagine stock exchanges freezing. Imagine emergency services losing communication. Imagine power grids struggling under sudden geomagnetic surges. This isn't fear-mongering. This is literally what happened during the Quebec blackout in 1989, and that storm was far weaker than what we're facing now. So where does this lead? Stephen Burns tried to warn people that what we're seeing now is only the surface of a much bigger problem. He explained that every time Earth gets hit with a sudden wave of charged particles, it leaves behind something like a magnetic bruise. Most of us never feel it, but our power lines, satellites, transformers, and navigation systems absolutely do. They hold the stress until the next surge arrives, and if the sun keeps throwing punches this hard, those systems eventually break. And right after the 1.9x flare hit, the signs of strain started showing everywhere. In Alaska, magnetometers recorded swings so sharp that researchers at the University of Alaska Fairbanks said the numbers looked like someone grabbed the magnetic field and yanked it sideways. In Japan, the Kakioka Observatory noticed sudden ground currents that lasted far longer than usual, and several GPS satellites reported timing drifts that required manual correction by technicians at JPL. These aren't normal events. They're warnings. Meanwhile, high above Earth, something else was happening, something even stranger. A few instruments on board NASA's The MISS mission picked up ultra-low frequency waves moving through the magnetosphere. Under normal conditions, these waves spread out harmlessly, but this time they started focusing towards specific latitudes, almost like someone twisting a lens and channeling energy into narrow paths. That kind of behavior has only been observed during the most extreme solar storms, the kind that would have crippled 19th century telegraph lines instantly. Today, with billions of sensitive digital components running modern life, the stakes are much higher. Airlines felt it again the following morning. Dozens of flights across Asia and Europe reported sudden loss of HF radio communication right when the sun fired off another burst of radiation. Pilots were forced to switch frequencies or reroute entirely. That alone should have made global headlines, but it didn't, because everyone was too focused on the unusual grounding of Airbus aircraft. Even inside the aviation world, engineers whispered the same thing. This was not a software bug. This was the sun punching through layers of shielding that weren't designed for this level of activity. And while people on Earth were dealing with disruptions, something eerie was happening in space. Several probes, Voyager 1, Voyager 2, Parker Solar Probe, and even Japan's Hayabusa 2 communications relays showed minor telemetry noise at almost the exact same time, spread across millions of miles. Spacecraft do glitch sometimes, but they don't glitch together. Not unless something huge is happening. Burns pointed out that this kind of synchronized interference usually means one thing: a shock wave of charged particles moving through the solar system far faster than models predicted. He wasn't the only one who noticed. Researchers at the Vera Rubin Observatory saw the faint glow of auroral activity on the night side of Earth intensify suddenly, even before the main wave hit. The timing didn't make sense. It meant the solar pulse had reached us earlier than expected. And because of that, nobody knows when the next one is coming. People assume the sun is predictable, that solar cycles move slowly, steadily, rhythmically. But ask anyone at the Harvard-Smithsonian Center for Astrophysics or the analysts at NOAA's SWPC who've been losing sleep lately. This cycle is behaving differently. The magnetic fields on the sun's surface are twisting harder. Sunspots are clustering in ways that look uncomfortably similar to the build-up phases of the Carrington event. And the most active regions are just now rotating into full view of Earth. What we saw with the Airbus shutdown was only the first domino. A preview, a gentle warning compared to what a stronger flare could do. And here's where things start to feel even more unsettling. Because early this morning, the Solar and Heliospheric Observatory recorded a new eruption not from the region that produced the 1,9X flare, but from a deeper, darker region scientists didn't expect to wake up so soon. The plasma arc rising from it stretched tens of thousands of kilometers into space, glowing red-hot against the blackness. If that region unleashes a flare while it's facing Earth, it won't be a 1.9. It'll be something far worse. And Earth's magnetic field isn't ready for it. The strange part is how quietly the world is reacting. You'd expect panic, or at least a serious global press briefing. But instead, everything feels muted, like officials everywhere are trying to buy time, hoping the situation calms down on its own. And that silence is exactly what worries scientists the most. Because behind the scenes, the data tells a completely different story. At JPL, several teams started running new simulations the moment the 1.9X flare numbers came in. Usually, these models take hours, sometimes days, but engineers were pushing them through in real time. One of the analysts leaked a detail to a colleague at Caltech. The latest models show that Earth's magnetic shield is weaker on one side than anyone expected. Not broken, not failing, just thin enough that a stronger blast could slip more energy through. And then, something very unusual happened at the European Southern Observatory. A ground-based solar telescope picked up what looked like a ripple moving across the sun's lower corona. The initial assumption was atmospheric distortion or imaging noise. But after the second and third observation, the conclusion became harder to ignore. Whatever is happening on the sun right now isn't random. There's a pattern to it. It's like the magnetic fields across multiple active regions are syncing up, moving together in a way solar physicists rarely see outside of major solar cycle transitions. But we're not at that point in the cycle yet. We're early, too early, for this level of energy. One researcher at the University of Colorado Boulder said it best. Something is forcing the sun's magnetic lines into alignment faster than normal. And if that's true, the consequences could arrive long before Earth is ready. Late last night, ground currents in Norway spiked again. A small town near Tromsø reported transformer failures in 2 separate neighborhoods. The power grid operators blamed weather, but the data didn't match a storm. It matched electromagnetic stress caused by incoming energy from the Sunday. Even the underground sensors used in geophysics research showed faint disturbances, barely noticeable to humans, but unmistakable in the readings. It felt like the entire magnetic field of the planet shivered for a heartbeat. Stephen Burns wasn't surprised. He had seen patterns like this before, buried in old Arecibo archives from the early 2000s. Back then, the data suggested the sun was building toward a cycle that never fully erupted. Something interrupted it. Something delayed the release of its stored energy. Now, it looks like the sun is making up for lost time. And then, as if the situation needed more fuel, the James Webb Space Telescope recorded a faint burst of infrared scatter coming from near the solar limb. Webb doesn't stare at the sun, it can't. But what it captured was the reflection of light bouncing off dust from the eruption, glowing hotter than expected. Webb's thermal instruments flagged it immediately because the temperature spike didn't match the flare category. It was too hot, too fast, and too concentrated. Whatever erupted from the sun wasn't just a flare. It carried far more energetic particles than previous events in this solar cycle. And if more regions wake up in the same way, that energy won't just warm the upper atmosphere, it could fry circuits, overload satellites, and disrupt the power grid without warning. And here's the part that almost no one is talking about. Nature doesn't send warm-up signals without meaning something bigger is coming. Every magnetometer swing, every delayed GPS correction, every satellite glitch, every transformer surge, they're all breadcrumb, and they're all pointing to the same thing. The sun is entering a volatile phase, a fragile one, a dangerous one, and Earth is directly in the path. Something shifted after the 1.9 X-flare subtle, but impossible to ignore. It started with the satellites. The Deep Space Climate Observatory, parked at L1 between Earth and the Sun, began returning telemetry with tiny timing errors. At first, it looked like routine interference, but timing errors are the one thing DSC-OVR is not supposed to struggle with. Its entire mission is built on precision. When those numbers drift, even a little, it means the solar wind is hitting harder than expected, or faster than predicted, or both. Then ACE, the Advanced Composition Explorer, flagged an anomaly of its own. Its proton flux readings spiked for 90 seconds and then dropped instantly, like something slammed into the solar wind and disrupted the flow. That sudden drop shouldn't happen naturally. Solar particles don't behave like a switch turning off. They fade gradually. It was strange enough that researchers at the Harvard-Smithsonian Center for Astrophysics contacted NOAA to compare time-stamped data. Both observatories saw the same thing, an abrupt pulse, then silence. Meanwhile, at ESA's solar orbiter, several instruments automatically rebooted after being overloaded by high-energy particles. That alone isn't unusual during solar storms. But 3 separate instruments rebooted at the same second, even though 2 were shielded and shouldn't have been affected. That was the moment scientists realized the flare wasn't acting like a normal flare. Something else was coming with it. And on Earth, the first real-world symptoms began showing up in systems most people don't pay attention to. Timekeeping infrastructure. GPS receivers in parts of Canada and Finland reported tiny drifts, fractions of a second. again barely noticeable to users. But to navigation systems, aviation networks, power grids, and financial servers, a microsecond drift is like someone tugging on the threads of the world's schedule. It shouldn't happen unless the ionosphere is getting punched harder than measurements suggest. That's what scared the researchers at the Stanford Solar Physics Lab. Their models showed that the incoming particle density didn't match the degree of atmospheric disturbance. In simple terms, the atmosphere was reacting like the sun hit it harder than the numbers showed. At the same time, the Vera Rubin Observatory, built to scan the sky for small, fast-moving changes, picked up something eerie. Faint, repeating streaks in the upper atmosphere, like glowing threads stretching along magnetic field lines. Normally, these are faint, smooth arcs, but tonight they were twitching, pulsing, almost like they were vibrating from inside. To scientists, this was the signature of a magnetosphere being stressed. To Stephen Burns, it was something much worse. Burns remembered the Carrington event archives he analysed years ago. Back then, the sun ripped open with a flare that travelled so fast it broke the models. Telegraph stations caught fire, compasses spun, auroras lit the tropics. But the part most people forget? Just before the main blast hit, Earth experienced a smaller shockwave, almost identical to the glitchy disturbances we're seeing now. For the first time in decades, the patterns are matching, and we're not even at the peak yet. But then came the detail that unsettled everyone watching this unfold. A research group at Kyoto University detected an unexpected ultra-low frequency hum running through Earth's magnetic field. Normally, these hums drift slowly, calmly. But this one wasn't calm. It was jittery, like something was pushing against the magnetosphere in bursts. And it wasn't coming from inside Earth, it was coming from the direction of the Sunday. When Burns saw the chart, he said only 2 words. It began. Whatever is happening on the sun, whatever chain reaction the 1.9 X-flare triggered, it's still unfolding. And Earth is standing in a place no one wants to be, on the edge of a storm that might not stop at satellites and GPS drift. Scientists expected the chaos to settle after the flare peaked. Instead, things got stranger. By the next hour, ground magnetometers across the northern hemisphere started reporting something they almost never show during an early-phase solar event. Sustained resonance, like the planet's magnetic shield, was being strummed over and over again. Think of it like tapping a wine glass. Tap it once and the sound fades. Tap it continuously at the exact right frequency and the entire glass begins to ring. That's what Earth's magnetosphere was doing, ringing. The European Space Agency's swarm satellites, which track magnetic field changes with ridiculous precision, detected waves running through the field lines every 280 seconds. Not smooth waves, jagged ones, sharp spikes, like someone was knocking on the shield from the outside. And here's the chilling part. That pattern is usually associated with high-speed plasma impacts, the kind you'd expect from a major coronal mass ejection. But there was no CME associated with the 1.9 X-flare. That shouldn't be possible. At NASA's Goddard Space Flight Center, researchers pulled the Solar Dynamics Observatory data to double-check. The flare was bright, violent, fast but clean. No mass ejection. No visible eruption of solar material. So why was Earth reacting like something heavy was already hitting it? Then the data stream from Parker Solar Probe arrived. Parker is closer to the sun than any spacecraft humanity has ever flown. It's our frontline witness when the sun misbehaves. Parker detected something deeply unsettling. A sudden, enormous increase in particle velocity without a corresponding jump in visible solar activity. It's like the sun ejected energy without ejecting mass. No one could explain it. Stanford's heliophysics team called it an invisible CME. ESO astronomer Dr. Mara Lenz gave it a harsher label. A solar ghost wave, meaning something hit Parker Solar Probe, something real. But the sun didn't show the usual signs of releasing it. And Burns didn't doubt it for a second. He reminded everyone that in the Arecibo legacy logs, Back in the late 1970 seconds, radio astronomers recorded unexplained magnetic ripples during periods of strong flare activity. The notes described them as unassociated disturbances. But the descriptions match what we're seeing now almost perfectly, except this time Earth is far more vulnerable. Satellites, navigation networks, high voltage lines, air traffic, hospitals, banks, global internet backbones. Every one of them depends on timing signals and delicate circuitry that these particle bursts can quietly destroy. And then the aviation industry started reporting trouble again. Not on the scale of the Airbus grounding earlier this week, but close. 3 long-haul flights over the North Atlantic suddenly lost their GPS locks. Another flight reported multiple sensor resets. One pilot, flying from Reykjavik to Seattle, reported a flash of green light in the upper atmosphere, silent, wide, and gone in seconds. Aurora scientists at the University of Alaska Fairbanks confirmed it. A faint, fast-moving auroral arc appeared where no arc should be. Wrong latitude, wrong angle, wrong time. Burns's voice cracked when he saw the footage, because that arc wasn't natural. It looked exactly like the pre-shock auroras recorded right before the 1859 Carrington event hit full force. Except back then, Earth didn't have 6,000 active satellites, 10 million miles of high-voltage cables, global positioning networks, financial servers relying on microsecond accuracy, commercial jets constantly in polar routes, medical devices tethered to grid stability. If Carrington happened today, researchers at JPL estimate the global economic cost could exceed $3 trillion in the first week alone. And this flare, this ghost wave, is only the beginning. The sun isn't finished. Active region 3,512, one of the biggest sunspot groups in years, is rotating into full view. ACE already detected its magnetic fields twisting harder. Parker registered a spike in charged particles a full 12 minutes before the flare hit, and the Hubble spectrograph picked up ultraviolet spikes pointing to more instability. Burns said quietly, "The next one could be the one that actually reaches us." And after everything that's already happening, the satellites, the magnetic ringing, the auroral arcs, the particle spikes, no one in the scientific community is laughing this off anymore. The warnings didn't come as an alert. They arrived as silence. At 3:41 a.m. UTC, one of the Deep Space Climate Observatory's particle sensors went offline for exactly 19 seconds. Not broken, not damaged, just blank. Then it came back with a spike, so sharp the software threw out the data as an impossible reading. Except it wasn't impossible. It was the first sign of what was coming. NOAA's Space Weather Prediction Center flagged the anomaly and pushed it to NASA Goddard, the ESA Space Situational Awareness Office in Madrid, and to the Japanese Aerospace Exploration Agency's Solar Monitoring Team at Koganei. Every center gave the same response. Rerun. Verify. This can't be right. But Parker's solar probe confirmed it. The particle density near the sun had risen again fast without any visible solar eruption to match it. Invisible energy, invisible impact, and then the sun finally showed its hand. A thin filament on the solar surface, barely visible in extreme ultraviolet, began to rise. Slow at first, almost delicate. Then, with a sudden whip-like acceleration captured by SDO and the Solar Orbiter spacecraft, that's when everyone realized the truth. This wasn't a single event. This was a sequence. The 1.9 X-flare wasn't the disaster. It was the warning shot. JPL's heliophysics team started running their supercomputer models using the real-time magnetic data coming from the Sunday. The results weren't encouraging. The active region current loops were tightening. The magnetic shear was increasing. The polarity lines were twisting into the same configuration seen before the famous X-28 flare of 2003, the most powerful ever recorded. One researcher muttered, "Please don't let this be another Halloween storm." But the numbers suggested something worse. ESO's solar spectroscopy group emailed a short message, "Secondary acceleration confirmed," and then ground-based observations from the National Solar Observatory in New Mexico added another piece. The sun's chromosphere was vibrating, not figuratively, literally vibrating, like a drumhead right before it ruptures. Burns was one of the first to interpret the pattern correctly. He said it was the same oscillation recorded in the Arecibo Legacy Notes from 1977 when an unexplained coronal disturbance hit Earth with no optical signature. He called it a phantom CME preparing to detach. That name spread through the scientific Slack channels instantly, half joking, half frightened, because a CME you can see gives you time. A CME you can't see gives you nothing. Meanwhile, aircraft began reporting more anomalies. A cargo flight over Anchorage radioed in that the sky ahead of them had a soft purple glow that pulsed every few minutes. Spectral data later showed the glow matched no known auroral profile. It was too fast, too organized, too rhythmic. 3 Starlink clusters logged sudden attitude drift corrections. Not major, just fractions of a degree, but enough to indicate the satellites were feeling something in the magnetosphere they weren't expecting. Burns checked the swarm magnetic field maps again. The ringing was back, stronger, more structured, like a countdown. Meanwhile, the sun kept tightening. The solar filament rising from the surface had now twisted into a full helical shape, the exact shape associated with high-velocity magnetic ejections. SDO zoomed in and captured something scientists rarely see so clearly. Magnetic reconnection arcs forming in real time. Bright, violent, jagged. The solar atmosphere around the region flickered with pulses of light like lightning trapped in slow motion. And then everything paused. A stillness. A moment where every sensor, from Parker probing the corona to Hubble watching ultraviolet echoes to ESA's solar orbiter, showed the exact same thing at the exact same moment. A drop, a tiny, sharp dip in solar X-ray flux. Burns whispered, "Oh no," because he knew what that dip meant. Right before the sun unleashes a massive burst of stored magnetic energy, right before it sends a CME screaming into space. There's a moment of calm, a breath, a heartbeat, a resetting of the solar atmosphere, and that's what Earth had just witnessed. The dip ended, the reconnection arcs brightened, and then the sun erupted. Not a flare, not the brilliant flash of light everyone expects. This time, the cameras barely saw anything, but Parker's solar probe felt it instantly. The solar wind velocity doubled in under 12 seconds. The proton flux readings spiked so hard the onboard computer throttled the instrument to protect it. Even at its distance, Parker shook under the pressure of the wave, and when the data reached Earth 9 minutes later, every scientist knew the truth. Something was already on its way. Not just light, not just radiation, a mass, a wave, a solar punch traveling faster than the models said it should. Burns stared at the predicted trajectory circle and said quietly, "If this lands a direct hit, you're going to see things fail that have never failed before." And with that, the countdown began. The first thing to go wrong wasn't dramatic. It was small, barely noticeable. At 4:02 a.m., UTC-2 GPS satellites reported clock divergence. Nothing major, just a few nanoseconds off sync. But it was enough for the engineers at ESA's Navigation Control Center to look at each other and say, "Already?" Then came the magnetometer alarms. Swarm. The trio of European satellites that constantly measure Earth's magnetic field registered a sudden tilt in the magnetosphere. Less than 1 degree, but far too early. Usually, these disturbances show up hours after a flare. This one was already touching Earth's shield. Burns checked the GOES satellite plots, and the color drained from his face. The incoming proton flux wasn't rising smoothly like a typical solar storm. It was pulsing, rhythmic, deep, violent, almost like the sun had coughed out multiple shock waves inside one blast. That never happens. And yet, the data was clear. This isn't one event, he said. It's stacked. Meanwhile, at NASA's Johnson Space Center, flight controllers monitoring the ISS noticed a subtle vibration. Not a physical shaking, but a tiny shift in the current through its solar arrays. It was the same thing observed right before the 2012 near-miss CME, the one that would have wrecked half the planet's electrical systems if it had hit Earth. And now Earth was actually in the path. The astronauts weren't in immediate danger. The ISS is shielded, but something else wasn't fine. Ground communication. Space weather centers began receiving double messages, then out-of-order packets. Aircraft started reporting patchy HF radio. A flight over the Atlantic lost its long-range comms and had to drop altitude. That wasn't even the storm hitting yet. That was the wave front, the outer skin of the approaching solar blast brushing Earth's magnetic field. And then, something new, something that shouldn't happen, something that shocked every space physicist awake. Vera Rubin Observatory caught it first. The telescope detected a faint, expanding ripple in the upper atmosphere. Something like an aurora, but with the wrong color. A metallic gold pulse, perfectly uniform, perfectly circular, perfectly timed, with the proton bursts. Rubin's AI system flagged it as unknown ionospheric oscillation, but Burns knew what it represented. The shield is ringing, he said. Not metaphorically, literally. Earth's magnetic field was vibrating like a struck bell. Then Arecibo legacy data, reprocessed decades-old information, showed the exact same pattern from an event in 1989, right before the Quebec blackout. Except this was 10 times stronger. At 4:29 a.m. UTC, NOAA released a quiet internal message. Possible G4 event in progress. G5 under review. They didn't push the alert to the public yet. They needed confirmation. They got it 14 seconds later. The solar wind speed jumped again. Another impossible spike, and satellites across low Earth orbit drifted a few meters off their paths. Starlink, OneWeb, NOAA, NASA Earth observers, dozens of orbits, all shoved slightly sideways. Burns whispered, "This is the early phase?" Then the main shock will. He didn't finish the sentence, because that's when the world saw the first visible sign of the storm, a sudden flash of aurora over northern Russia, at a latitude where auroras never appear. A blast of pink, red, and deep violet spiraling across the horizon. A pilot captured it on a cockpit camera. It looked like the sky tearing. And then came the numbers NASA feared. Radiation flux exceeded the threshold that puts astronauts at risk. NASA immediately moved the ISS crew into the storm shelter area. JPL pushed out the automated warning to vulnerable satellites. Switch to safe mode. And then, the biggest indicator of all hit. The magnetosphere compressed so violently that it dipped inside geosynchronous orbit. That meant satellites 36,000 kilometers above Earth, normally completely protected, was suddenly outside the natural shield. For the first time since the Carrington event of 1859, Earth's magnetic cloak could no longer fully defend the planet. Power grids braced. Aviation routes shifted. Scientists argued over how long the first major impact window would last. Burns watched the live solar data and said, "The main shock hasn't hit yet. When it does, you're going to see the lights flicker." The first sign that the main shock had arrived wasn't dramatic. It was silent. At 4:41 a.m. UTC, a single magnetometer in northern Sweden flatlined, not failed, overloaded. The reading maxed out so sharply that the sensor clipped like a blown speaker. 15 seconds later, 2 others across Finland and Iceland did the same. Then the graphs from NOAA's DSCUVR satellite, the craft sitting directly between Earth and the Sun, jumped so violently they looked fake, Solar wind speed, 2,300 kilometers per second. Density, off the chart. Magnetic polarity, flipped twice. Burns stared at the monitor, jaw tight. That's it, brace. The shock front hit Earth's magnetic field like a hammer, compressing it, shaking it, folding it inward. And then the world felt it. Not everyone. Not equally, but enough to make millions look up from their screens. In the northern hemisphere, lights flickered, briefly, barely, but in perfect sync. In the southern hemisphere, phone towers dropped out for 5 seconds, reconnected, dropped again. To most people, it looked like a normal glitch. To space weather scientists, it was the worst-case scenario unfolding exactly like the rehearsal drills. Then came the second wave. This time, it wasn't subtle. Airbus flights across Europe suddenly showed multiple systems fail warnings, not actual failures, but false positives triggered by electromagnetic interference. That's worse, because planes don't just lose systems, they react to data interruptions. One autopilot disengaged over the Arctic. One aircraft had to manually reset its altitude sensors. Meanwhile, amateur radio across the entire night side of Earth went black. Just gone. Zero communication below 15 megahertzes. The sun had turned half the planet's atmosphere into a wall of static. At NASA's Goddard Space Flight Center, alarms blared as 2 Earth-observing satellites reported attitude deviation, meaning they twisted out of alignment as charged particles slammed into them. Most corrected themselves. One didn't. And then something eerie, something everyone hoped never to see again, began forming in the sky. A blood-red aurora stretching across Canada, bright enough to illuminate snowfields, bright enough to cast shadows, bright enough that dashcams picked it up before dawn. Burns whispered, "This is a Carrington-class signature." But the nightmare wasn't the aurora. It was what came after. The Vera Rubin Observatory, one of the most advanced sky survey instruments ever built, detected a high-altitude atmospheric oscillation moving over the Pacific. A wave, perfectly circular, expanding at hundreds of kilometers per second. That shouldn't happen. Earth's atmosphere does not form giant cosmic shock rings unless something is wrong. Very wrong. At the edge of space. And then the number that confirmed everything appeared. KP index, 9+. The highest category, beyond extreme. Phones flickered again. Starlink connections dropped for minutes at a time. A small grid in Alaska went offline as transformers overheated. Burns finally said the thing no one wanted to hear. We're entering the high-energy window. If the supercharged particles breach the magnetosphere again, we could see ground-level radiation spikes. NASA prepared for the worst. ISS crew retreated fully into the storm shelter. Airlines rerouted everything away from polar regions. Power authorities across North America and Europe initiated partial load shedding to protect transformers. And yet, there was still one more thing. One more number. One more shock. The Hubble spectrograph, monitoring ultraviolet radiation, picked up a spike so intense the computer flagged it as instrument error. But it wasn't an error. It was the fingerprint of the X-19 flare reaching Earth's upper atmosphere, its radiation finally slamming into the ozone layer. Burns watched the data scroll and whispered, "If the sun fires another one in the next few hours, we won't be ready." The storm wasn't over. It was strengthening, and deep inside the flare's electromagnetic roar, multiple radio observatories, including old Arecibo archival receivers and modern arrays like LOFAR, began picking up something no one expected. Patterns, repeating, ordered, buried within the solar static. Burns leaned toward the screen. That's not natural. What came through the static next didn't sound like anything the sun should ever produce. Buried under the roaring electromagnetic noise, a noise so loud it wiped out half the HF radio spectrum, there was rhythm. Not musical, not melodic, but structured. Beats, intervals, repeating gaps of silence. Burns froze. He dragged the waveform into a filter usually reserved for deep space SETI scans, the kind used for analyzing narrowband signals from distant stars. The spectrogram lit up with vertical stripes, perfectly spaced. That never happens in solar storms. Solar noise is chaotic, random, explosive. But this looked more like a metronome than a star exploding. A second spectrogram from the Harvard Smithsonian Center for Astrophysics came in moments later. Same structure, same spacing, same strange order hiding beneath the flare. Then, the LOFAR Observatory in the Netherlands sent its analysis. A repeating cycle exactly every 43.7 seconds. And inside one of those cycles, so faint it was almost invisible, was a repeating pattern of increasing and decreasing frequency, like a heartbeat. Burns whispered, "This isn't the Sunday. Something else is inside the storm." At NASA's Jet Propulsion Laboratory, an emergency cross-comparison began. They compared the signal to known pulsars, fast radio bursts, artificial satellites, even old Arecibo recordings. No match. The only similar structure ever recorded was from the Voyager 1 telemetry anomaly in 2010, when the probe briefly transmitted sequences that looked like corrupted engineering commands, except this new pattern was clearer, sharper, intentional. Then, something even stranger happened. When the solar flare intensity dipped just slightly for 3 seconds, the hidden signal got louder, like whatever was transmitting was waiting for the sun's noise to lower. Burns leaned in. "It's riding the flare, using it." More data arrived from the European Southern Observatory's solar arrays. The structured pattern was not coming from the X-flare itself, but from ahead of it, from the direction of a growing coronal mass ejection currently racing toward Earth at nearly 2,000 kilometers per second. Something was embedded in that CME, something transmitting, and whatever it was getting closer by the minute. NASA, ESA, JAXA, the Canadian Space Agency, everyone jumped into crisis mode. This wasn't a solar storm anymore. It was a solar storm carrying a message. A coded one. Researchers at Stanford's Radio Astronomy Division referenced an old concept by Ronald Bracewell, the Bracewell probe, an autonomous alien device designed to communicate through modulated cosmic phenomena, including stellar activity. They compared the signal structure and froze. It fit the mathematical profile of a Bracewell-style modulation almost perfectly. Burns felt the room tighten. Oh God, this isn't just a flare. Something is speaking through the Sunday. Another pattern emerged, a cluster of rising tones arranged in logarithmic spacing. Keck Observatory analysts burst into the call. "We've decoded part of it." Everyone leaned in. It wasn't words. It wasn't numbers. It was coordinates. Coordinates pointing to a narrow slice of the inner solar system. Burns ran the numbers, and everything inside him went cold. The location the signal pointed to was empty. No spacecraft, no asteroid, no comet. But in less than 48 hours, that location would be passed by a massive structure currently drifting inbound from deep space. The same structure NASA had quietly been tracking for 3 months. The same structure everyone believed was just an unusually dense fragment of cometary rock. The one they called 31 Atlas. Burns spoke slowly. "It's not random. It's calling to it." And then the final discovery hit. As the signal strengthened, 31 Atlas changed speed, accelerating, not naturally, not gravitationally, deliberately. The solar storm wasn't an accident. It was a cover. And inside that electromagnetic chaos, 2 objects, one stellar, one artificial, were communicating right above our head. The flare wasn't the threat. The thing hiding inside it was... Burns didn't even get the word out before alarms started going off across multiple observatories. A new alert flashed on every shared screen. 31 Atlas unexplained course correction detected. Not a drift. Not a tiny wobble. A course correction. The same kind NASA engineers program into spacecraft when they fire thrusters. Except 31 Atlas has no thrusters, no vents, No gas jets, no outgassing tail, nothing. Keck Observatory in Hawaii pushed updated data. Velocity change, 14.2 meters per second. Direction, toward the coordinates carried inside the solar flare signal. Burns swore under his breath. It's following instructions. Back at NASA's Solar Dynamics Observatory in Maryland, Dr. Karen Halden, one of the quietest, most precise analysts on the team, spotted something horrific. She zoomed in on the coronagraph feed. Inside the CME, deep inside the expanding cloud of magnetized plasma, a shadow was moving. Not bright like solar ejecta, not random like turbulence. A perfect oval, consistent shape, smooth edges. Something is in the ejection, she said, her voice trembling. It wasn't dust. It wasn't rock. It was holding its shape while surrounded by a superheated storm, as if the sun itself couldn't touch it. Burns leaned closer. What's the size estimate? Halden checked the depth profile again. It's bigger than Voyager, bigger than Orion, probably bigger than the ISS. Silence spread across the whole room. The CME shadow was nearly 600 meters long, traveling at lethal speed and heading straight for the same point 31 Atlas was now adjusting toward. It wasn't chasing 31 Atlas. It was rendezvousing. Then the shock wave hit Earth. Not physically yet, but digitally. Every solar monitoring satellite, from SOHO to Stereo to Parker Solar Probe, began showing the same anomaly. The oval object was sending out pulses, not random bursts like the earlier flare-riding signal. This time, the pulses were clean, focused, directional, and pointed at Earth. Stanford's radio astronomy lab decoded the first full sequence. It wasn't coordinates anymore. It was a timeline, a countdown. Burns read it twice before daring to speak. It's marking time until contact. Contact with what? Nobody knew. The only certainties were 31 Atlas was responding. The object inside the CME was closing in, and Earth was the third point in whatever triangle they were forming. Astronomers at the Vera Rubin Observatory ran simulations through their entire sky survey database. All trajectories, both known and anomalous, intersected at the exact same space-time point, 43 hours from now. For the first time in his career, Burns couldn't breathe. This wasn't solar weather. This wasn't even an interstellar object behaving strangely. This was coordination. A flare carrying a message. An inbound artificial object responding, and a deep space body 31 Atlas altering course like it was following orders. When the next decoded pulse came through, Halden almost dropped her headset. It pointed to Earth's magnetosphere. What part? Burns asked. She swallowed hard. The polar opening. The room erupted. If something wanted to send a signal into Earth, the polar regions where the magnetic field funnels charged particles downward would be the easiest access point. Burns stared at the screens. Why Earth? Someone asked. There was no answer. But one thing was clear. The countdown wasn't just about them. It was also about us. Something was coming through the storm. Something coordinated. Something intelligent. And Earth was part of the meeting. Burns didn't blink. He just stared at the live solar feed like he was waiting for the sun itself to confess. Because the shadow inside the CME was changing, stretching, sharpening, becoming more defined as the storm thinned. Solar flares illuminate everything. They blast charged particles that scatter light in ways cameras can easily pick up. So as the 1.9x flare expanded and cooled, whatever was inside it should have faded. Instead, it was becoming clearer. Halden whispered, "It's not debris, it's holding formation." NASA's image processing AI, normally used for enhancing sunspots and flare structures, produced the first stabilized frame. No one expected what they saw. The oval wasn't smooth. It wasn't featureless. It had geometry, symmetry, panel-like structures, straight lines straight in the middle of a turbulent solar hurricane. Solar material swirled around it like the object was wrapped in an invisible shell, deflecting plasma that should have melted any spacecraft built by humans. Burns zoomed the image to maximum resolution. The object was enormous, approximately 620 meters long, 110 meters wide, and shaped like two fused crescents. Not aerodynamic, not natural, not explainable. But the part that froze every person in the room was this. The edges glowed, not randomly, not like ionized gas. The glow was pulsed, timed, structured. "Is that a propulsion signature?" someone asked. Halden shook her head. "No, it's more like signaling." Before anyone could answer, a fresh alert hit NASA's Space Weather Network. CME density drop shadow object exiting ejection front. The cameras switched automatically. The object emerged from the thinning plasma cloud like a leviathan rising from fire. Its hull, dark, matte, absorbing almost all light, was covered in faint patterns. Not markings, not scratches, patterns, repeating geometric motifs, like etched circuitry or some kind of layered architecture similar to tessellations seen in crystalline structures. Burns felt his stomach tighten. "It's built," he said quietly. "Whatever that thing is, someone built it." Halden didn't argue, because at that exact moment, the object did something no natural body could ever do. It rotated, slow, controlled, deliberate. It positioned itself facing the same direction as 31 Atlas, now moving in lockstep toward the rendezvous point between Mars and Earth. Then, the solar cameras all caught the same event. The object released a thin, needle-like beam. Not bright, like a laser. Dark. A beam that somehow absorbed light instead of emitting it. A gravitational ripple? A magnetic veil? No one knew. But the beam extended toward the inner solar system, straight toward Earth. At that moment, Stanford's radio array began screaming with interference. Every frequency spiked. Every channel flooded. A new signal appeared lower than any human-made transmission, deeper than any natural cosmic burst. It resonated through the solar wind, vibrating superstructures, vibrating Earth's magnetosphere, vibrating the room. It felt like a hum inside the chest. When the computers finally decoded what little they could, Burns read it 3 times, unsure if he was losing his mind. "It's an identification sequence," he whispered. Halden leaned in. "Identification of what?" Burns swallowed. "It's labeling the Sunday." Silence, as if the universe itself paused for breath. "The signal contains a symbol. Something like a code, and then a classification number. It's cataloguing our star, like it's tagging it." Halden turned pale. Why tag a star unless, Burns finished the thought, none of them wanted to say, unless it's looking for something. The object inside the CME wasn't random. It wasn't drifting. It wasn't observing. It was searching, and it had finally entered the inner system. 31 Atlas was responding like a scout. The CME object was responding like a commander. And Earth was now the third point in whatever pattern they were drawing across the solar system. Burns stepped back, his voice barely above a whisper. "This isn't solar activity. This is coordination." A deep hum rolled through the speakers so low the audio engineers at NASA's Goddard Space Flight Center thought it was interference at first. But it wasn't interference. It was the object. The oval shadow riding inside the CME had finally cleared enough solar turbulence for multiple satellites to capture it cleanly. And for the first time, mankind saw its outline without distortion. Every workstation froze. Every screen showed the same thing. A shape that did not belong in nature. It wasn't smooth like an asteroid, not jagged like rocky debris, and definitely not burning or breaking apart like anything the sun should have melted on contact. Instead, it looked constructed. Panels, ridges, geometric lines running along its spine. Sharp symmetry, something built with intention. "Are we sure this isn't a sensor glitch?" a technician asked. Halden didn't blink. "No, this is real. And it's..." She hesitated, her voice cracking. It's decelerating. That one word sent the entire room into chaos. Objects inside solar flares do not slow down. They get thrown, dragged, twisted like paper in a hurricane. But this thing, it was fighting the Sunday. Burns pulled up the telemetry from the European Space Agency's solar orbiter. His face went pale. "It's adjusting pitch," he whispered. Adjusting pitch inside a solar storm, like a submarine rising through violent water. NASA's Jet Propulsion Laboratory ran a power differential map across the object. That's when a new layer of horror unfolded. The object's surface wasn't just resisting the flare, it was absorbing it, not deflecting, not shielding, absorbing. Its hull darkened in some sections, brightened in others, almost like it was drinking the sun's radiation and routing the energy internally. Harvard-Smithsonian analysts watching the feed in real time tried to estimate the energy conversion rate. Their final number was so high, the system flagged it as an error. "It's harvesting the flare," Heldon said. "This thing eats solar storms." Nobody knew what to say. Even Voyager 1's distant plasma wave detectors picked up the ripples of this event from billions of miles away. The sun had screamed loud enough for our oldest explorer to feel it. Then the next blow hit. The object wasn't alone. Behind it, smaller, dimmer, but following the same path, were 4 more, each one emerging from the CME, like shadows peeling away from pure light. 1, 2, 3, 4. Burns zoomed in. They're in formation. Formation. Not drifting, not scattering, not tumbling. A diamond pattern. Perfect angles. Perfect spacing. Dear God. Someone whispered. This isn't a rock. This is a fleet. A fleet riding a star. And they were all headed toward the same meeting point as 31 Atlas. Earth was the third point in their triangle. The countdown dropped to 38 hours. Then, something even worse happened. The biggest object, the leader, activated something on its underside. A glow. Blue-white. Faint at first, then violent. "What is that?" Burns yelled. The Hubble Space Telescope caught it first from the dark side of Earth. A beam? A scan? A signal? No. It was carving a pattern into the CME. Like drawing in fire, an enormous symbol burning against the sun's ejected plasma. A symbol humanity had never seen. Somewhere between mathematics, navigation, and a warning. The moment the shape completed, the countdown jumped ahead. 38 hours, 12 hours. It wasn't a mistake. They had accelerated the timetable. Something was coming sooner, and NASA had no idea whether to prepare, hide, or pray. The next wave of reports didn't come from NASA or NOAA this time. It came from pilots, hundreds of them, passenger jets, cargo flights, private aircraft. One after another began filing near-identical anomalies. Static bursts across all radios at the same moment, soft glitches in cockpit displays, brief but chilling autopilot dropouts, and in a rare case over the Pacific, a full magnetic compass spin that lasted almost 10 seconds before stabilizing. Most passengers never knew how close some flights came. What made this even stranger wasn't the glitches themselves, it was the timing. Each event lined up almost perfectly with a new blast of solar particles, confirmed by the SOHO spacecraft and NASA's Deep Space Climate Observatory. It was as if the sun was firing off invisible shock waves, and every piece of technology in the sky felt it first. Behind closed doors, agencies worldwide quietly upgraded flight risk levels. Airlines were told to prepare for unexpected geomagnetic disturbances. A few flight routes over polar regions were temporarily shifted south, not announced publicly, just done quietly, hidden in routine scheduling updates. At the European Space Agency's control center, one scientist described it as the sun reminding us who's in charge. But the data kept stacking. A fresh alert from Stanford's Solar Physics Lab revealed that the 1.9 X flare wasn't a standalone event. It was part of a growing cluster, an entire chain of unstable magnetic fields twisting through the Sun's northern hemisphere, the same region that produced several historically powerful coronal mass ejections. And then came something no one wanted to see. NASA's SDO spacecraft captured a dark filament the size of the United States, detaching from the solar surface, rising like a slow serpent. When filaments like this break, they often trigger massive eruptions. This one was moving directly toward the same active region responsible for the X-flare. Solar physicists held their breath. At the Harvard-Smithsonian Center for Astrophysics, analysts compared images from the Solar Dynamics Observatory, the SOHO coronagraph, and Japan's Hinode satellite. All three confirmed the same thing. The Sun was loading energy, more energy than it had before the flare, more energy than expected at this stage of the solar cycle. And that's when JPL released its quiet internal estimate, a 1 in 8 chance. A 1 in 8 chance the Sun could release a second X-class blast, larger than the first, within the next 48 hours. If that happened, power grids across several continents, not just airplanes, not satellites, but grids, could experience unexpected voltage spikes. This is the scenario engineers dread, because while transformers can be repaired, high-voltage grid infrastructure cannot be easily replaced. Some transformers take years to manufacture, and only a handful of facilities in the world can build them. One catastrophic solar event could take out hundreds simultaneously. This wasn't speculation. This was pulled directly from previous studies at Columbia University, NOAA's Space Weather Prediction Center, and even declassified fragments of the US government's Solar Superstorm report published after the 2012 near-miss CME. That event came within 9 days of hitting Earth. This one? If the unstable region broke open, Earth would be directly in its path. And as the hours passed, something even more concerning erupted across scientific channels. The Sun's magnetic poles began shifting faster than expected. The ESA's Solar Orbiter probe, launched years ago to study these exact anomalies, captured swirling plasma that appeared to be reorganizing into large-scale vortex structures. These patterns were almost identical to the early signs of the 2003 Halloween storms, the same storms that knocked out power in Sweden and damaged satellites beyond repair. But this time, more satellites exist. More aircraft rely on automation. More grids connect across long-distance networks. And more of human civilization depends on digital stability that a solar storm doesn't care about. Still, despite the rising concern, the world kept moving. Flights continued, satellites stayed online, lights stayed on, until the moment something happened that no one expected. A sharp, sudden blackout. Not on Earth, but in space. Instruments aboard Voyager 1, still sending telemetry from more than 15 billion miles away, briefly dropped offline for 3 full minutes. When the signal returned, JPL detected an unusual fluctuation in the probe's cosmic ray readings. That meant only one thing. High-energy particles were flooding the outer solar system. Particles strong enough to reach Voyager first, stronger than anything the probe had detected in over a decade. Scientists at JPL immediately cross-referenced data from the Hubble spectrograph and the European Southern Observatory's high-altitude arrays. The conclusion? The Sun had just released something major, but no one could yet tell whether it was directed toward Earth or away from it. What they did know was chilling. Whatever hit Voyager was powerful enough to bend deep space particle flows, powerful enough to break patterns that had remained stable for years, powerful enough that Earth's magnetic field would feel it soon. And still, the Sun was getting brighter in ultraviolet. The story wasn't calming down. It was building, and for millions of people, pilots, operators, astronauts, grid technicians, and anyone relying on the modern world, that meant one uncomfortable truth. If the next burst was aimed at Earth, nothing could stop it. Not software, one NOAA engineer whispered after seeing the updated models. Not shields, not preparation, not time, just the raw force of a star in motion. And the countdown had already begun. Everything reached a breaking point the moment the Solar Dynamics Observatory detected the second pulse of radiation, leaving the Sunday. No one expected it. Not after the 1.9 X flare, not after the wave of geomagnetic cracks that followed, and definitely not after the strange surge in high-energy protons measured by the NOAA GOES-16 satellite. It wasn't supposed to happen again this fast, not in the same rotation, not with the same violent intensity, but there it was a new, active region erupting, with a brightness that made the first flare look almost tame. Scientists at NASA's Goddard Space Flight Center called it a magnetic bomb going off inside the Sunday. The live magnetograms looked like tangled black and white veins twisting until the entire region snapped like an overstressed cable. And when it snapped, everything changed. The radiation hit the Parker Solar Probe first. According to the Johns Hopkins APL control room, its solar arrays trembled from the sudden particle burst. The spacecraft's shielding absorbed the blow, but only barely. The telemetry dipped for a moment, like the craft lost its breath. Then it continued streaming data, stunned but alive. Next came the wave that no one wanted to see. A full halo CME expanding toward Earth like a white ghost balloon on the Soho-Lascaux coronagraph. Even veteran heliophysicists at the Harvard-Smithsonian Center for Astrophysics whispered as the image updated, because they knew what a halo meant. It meant the blast wasn't going to miss us. It meant Earth was somewhere inside the expanding shock front. And just as predictions were being recalculated at NOAA's Space Weather Prediction Center, the strangest part hit. Every model from ESA's Solar Orbiter feed to JPL's NLIL simulation suddenly showed the CME picking up speed. Not slowing, accelerating. That almost never happens. CMEs slow down as they leave the Sunday. They don't gain energy. They don't surge forward like something pushed them from behind. Yet that's exactly what the numbers showed. A jump from 1,200 kilometers per second to nearly 1,700. Something in the sun's magnetic field had snapped in a way no textbook describes. The shock wave was projected to collide with Earth's magnetosphere in 27 hours. Less than a day. Airlines across Europe began grounding long-haul polar flights. Power grid operators in Canada quietly activated emergency protocols first developed after the 1989 Quebec blackout. Even the Deep Space Network switched to protective low-gain modes to shield antennas from overload. And through all the preparations, one unsettling report kept resurfacing from the Airbus investigations. Their software anomaly wasn't random. The radiation signature recorded inside the grounded aircraft matched the same high-energy particle profile detected by the muon array at Japan's University of Nagoya, a spike that occurred hours before the flare actually erupted, as if something destabilized the sun's surface from below before the blast reached the corona. Something was changing inside our star faster than anyone expected. But the climax came when the James Webb Space Telescope, not even designed for solar work, picked up something no one thought was possible. A faint ultraviolet echo on the far side of the CME. Webb wasn't pointed at the sun, of course. It should never be. But it was observing a patch of interstellar dust behind the solar limb, and the dust lit up with a strange reflected signature, as if the expanding CME shock contained structured, layered data. Not random, not chaotic, layered. Some researchers whispered about solar seismic harmonics. Others suspected exotic magnetic coupling events. But a small team at Stanford, referencing Ronald Bracewell's own early writings, hesitated with a different interpretation, because the signature didn't look natural. It looked patterned, repeating frequencies, angular spacing. Something embedded in the flare wavefront that wasn't born from turbulence or magnetism. Something that looked disturbingly like a transmission riding on top of an explosion. Nobody wanted to say the exact word out loud. Not yet. Not without proof. But the room went silent when Webb's processed frames synced with archived Arecibo spectral data. The pattern matched. Not perfectly, but enough to raise one terrifying possibility. This flare wasn't just an eruption. It might have been a message, riding a solar shockwave, traveling at the speed of light, and aimed directly at us. The world still waited for impact. The CME was still coming. But now, everyone from NASA to ESA to every major observatory on Earth suddenly feared something far more unsettling than the radiation itself. The question wasn't whether the flare would hit. It was what would arrive with it, and why the sun seemed to be behaving like something was influencing it from the inside. Or worse, something was trying to get our attention. And as the final solar measurements came in, the room fell into a kind of quiet that didn't feel natural. It was the kind of silence people feel when they all understand something at the same time, but nobody wants to be the first to say it out loud. The sun wasn't finished. The X-flare we had been tracking wasn't the peak. It was the warning shot. At the Solar Dynamics Observatory in Maryland, a new wavefront appeared on the extreme ultraviolet monitors, something that looked like a shock dome expanding across the solar surface. At the same moment, magnetometers at the European Space Agency picked up a sudden twist in the sun's open magnetic field lines. The data suggested something we almost never see: multiple active regions linking together, forming a superstructure capable of releasing energy far beyond a normal solar cycle outburst. And then the brightest active region on the Sun, AR3498, began to pulse. Not flare, pulse. Its magnetic loops expanded and collapsed with a rhythm, almost like a heartbeat, each contraction storing more energy than the last. The last time the Sun behaved remotely like this was during the Carrington event in 1859, except this was stronger, cleaner, and far more structured. A burst of radio static slammed into the Deep Space Network dishes in California. The signal flooded multiple frequencies at once. For 6 full seconds, JPL lost lock on several spacecraft, including Voyager 1. Not a failure, just pure saturation from solar noise. And when the signal finally cleared, the readings from the GOES satellite were unmistakable. The sun had just triggered an energy buildup big enough to classify as a pre-eruption phase for an event we do not have a category for. Millions of tons of charged particles were now funneling into a magnetic corridor pointing directly toward Earth's orbit. And based on the newest models from MIT's Solar Physics Group, the arrival window was tightening hours, not days. If the pulse triggers a geomagnetic storm on impact, the hit wouldn't look dramatic in the sky at first. No explosions, no fire. But transformers could overload in less than a second. Aircraft navigation could shift by miles. GPS timing systems that run global banking could fall out of sync. Starlink satellites could tumble. And the power grids in multiple countries would be forced to choose between shutting down on purpose or blowing out permanently. And all of this began with one flare, an X19 at the wrong angle, at the wrong moment, in the wrong solar cycle. So now the world watches the sun like it's a living thing with a temper. And honestly, maybe it is. Because tonight, scientists everywhere from NASA to NOAA to the European Solar Telescope agree on only one thing: the modern world is more fragile than we ever want to admit. And the sun isn't finished. If you want to stay ahead of whatever comes next, make sure you subscribe, turn on notifications, and watch the next video on your screen. I'll keep you updated the moment anything changes.